Now we come towards force between two moving charges. Electric force acts between the two stationary charges, which is determined by Coulombs law. The Coulombs law is given as Fe, that is the electrical force, is equal to K Q1 Q2 over R square, where K is 1 over 4 pi epsilon naught, that is Q1 Q2 over R square. And the value of 1 over 4 pi epsilon naught is generally 9 into 10 to the power 9 Newton meter square per Coulomb square. If charge is not stationary, in that case magnetic field also acts in the direction of electric field. Each charge Q moves with velocity v, produces a magnetic field whose intensity at a point having position vector r will be V is equal to mu naught by 4 pi Q into cross product of V and R divided by R square, and that is found to be mu naught over 4 pi QV sin theta over R square. Position vector R is with respect to source charge. The fourth point is that if charges Q1 and Q2 are moving with velocities V1 and V2 respectively, and at any instant the distance between them is R, then force between them will be Fm is equal to mu naught over 4 pi Q1 Q2 into V1 V2 divided by R square newtons. If both charges are of the same nature and moving in the same direction, the magnetic force acting between them will be attractive in nature. If the two charges are moving in opposite direction or their nature are opposite, then magnetic force acting between them will be repulsive in nature. If both charges are moving with same velocity, then the magnetic force acting between them will be mu naught over 4 pi Q1 Q2 into V square divided by R square Newton. Wherever we write Q mu naught over 4 pi, this number can be replaced by a constant number 10 to the power minus 7. Because mu naught is 4 pi into 10 to the power minus 7, when it will be divided by 4 pi, the number comes as 10 to the power minus 7. That is, magnetic force acting between the charges depends upon their velocities. If an observer moving with velocity v observes a charge moving with same velocity v, then it will appear stationary. In that case, electric force will appear to be acting between the charges and not the magnetic force. Locate the figure. In the adjoining figure, this is indicated. One is the case of stationary charges and other is the case of moving charges. If charges are stationary and they are seen by an observer moving with velocity v, then both electric and magnetic force will appear to be acting between them. The existence of magnetic force acting between the two charges depend upon the motion of charges relative to observer. Thus, for observers moving with different velocities, the magnetic force acting between the two charges will appear different. Again, locate the figure. There are two parts of the figure. The above figure is for stationary charges and the below figure is for the moving charges. Next, ninth point. The ratio of magnetic force and electric force acting between two moving charges is Fm over Fe. That is magnetic force over electric force. Mu naught over 4 pi Q1 Q2 into V square over R square whole divided by 1 over 4 pi epsilon naught Q1 Q2 divided by R square equals to mu naught into epsilon naught into V square. You will remember that mu naught for air, medium or vacuum is 4 pi into 10 to the power minus 7 Henry per meter or Weber per ampere meter, and epsilon naught is 8.854 into 10 to the power minus 12 Coulomb square per Newton meter square. But mu naught epsilon naught is equal to 1 over c square, where c is the velocity of light in vacuum. And from this we can get the value of c, which is 1 over mu naught epsilon naught square root. This equation will be generally known as the Maxwell electromagnetic equation for the velocity of electromagnetic waves. You will remember that light is electromagnetic wave. Magnetic force over electric force will be V over C whole square. Again, you can look at the figures for the stationary charges and the moving charges. V is very less than C, then Fm is very less than Fe. The force acting between the charges is represented in the following figure. Example based on the force on two moving charges. A proton is moving in circular path perpendicular to some magnetic field of induction B. If value of B is doubled and radius of circular path is kept constant, then what will be the value of kinetic energy of the particle? Value of kinetic energy of proton. Proton is a charged particle having charge equal to E. Kinetic energy is half mv square, that is r square, q square, b square over 2 pi m. Then value of kinetic energy, if value of B is doubled, is given as follows. Kinetic energy nu, r square, q square, 2b square over 2m. And by calculation, it becomes 4r square, q square, b square over 2m, which is 4 times the initial kinetic energy. Second example is, in hydrogen atom, electron revolves around the proton in an orbit of radius 0.5 angstrom unit. If at the position of proton, magnetic field of magnitude 14 Tesla is produced, then what will be the value of angular frequency of the motion of electron? The magnitude of magnetic induction on proton will be B naught is equal to mu naught EF over 2R, where E is the electronic charge. Electronic charge is found to be 1.6 10 to the power minus 19 Coulomb. F is equal to B naught into 2R divided by mu naught E. Computing the values, and the final result will become 7 into 10 to the power 15. Now next is force and torque on a current carrying loop placed in uniform magnetic field. A rectangular conducting loop PQRS is placed in uniform magnetic field. Its length is L and breadth is B. The rotational axis of the loop is perpendicular to the magnetic field. When current I is passed through the loop, then resultant force acting on the loop is 0, but torque acts on it. You can check up the figure. PQRS is representing the conducting loop, and the direction of forces are given as F3 and F4, and one is F1 and other is F2. Magnetic field is indicated by parallel lines. When current I is passed through the loop, then resultant force acting on the loop will be 0, but torque will not be 0, it will act on it. If plane of the loop makes an angle alpha with the direction of magnetic field, then the torque acting on the loop is given as tau is equal to 1 I L B cos alpha. Tau will be equal to I L small b, then it is B cos alpha. B is magnetic induction. LB, length into breadth, is equal to area, that is area of the rectangular loop. So tau can be written as I B A cos alpha. If the loop has n turns, then multiply this function by n and it will become NIA B cos alpha. If the vector area of the loop makes an angle theta with the direction of magnetic field, then theta is pi over 2 minus alpha. Tau is given as I into AB sine theta. For n turns, we have to multiply the number by n and it will become NIAB sine theta. Again, you can look at the diagram. NIA is equal to M, that is magnetic moment of the loop. Tau is equal to MB sine theta. In vector form, tau is the cross product of M and B. However, in case of a magnet, you will remember that magnetic moment is magnetic length of the magnet, that is 2L normally, magnetic moment, multiplied by pole strength. So its unit can be Weber meter. The torque acting on a current carrying loop placed in magnetic field depends on its magnetic moment but not the shape of the loop. For maximum torque, theta is 90 degrees or alpha is 0. That is, the plane or the loop should be in the direction of magnetic field, or the vector area of the loop should be normal to the magnetic field. Tau maximum will be mb sine 90, that is equal to mb because sine 90 is 1. Again, look at the figure. Now, the seventh point is that for minimum torque, theta is equal to 0, alpha is 90. That is, the plane of the loop should be normal to magnetic field, or vector area should be in the direction of magnetic field. The minimum torque is mb sine 0, that is equal to 0. The eighth point is that torque acting on the current carrying loop placed in magnetic field depends on the current. Moving coil galvanometer is based on this principle. The work done in deflecting a coil from angle theta 1 to theta 2 is given by function W is equal to mb cos theta 1 minus cos theta 2. Locate the figure. The work done in deflecting a coil from an angle 0 to theta in the magnetic field, W is equal to mb into 1 minus cos theta.